Okay, we're going to begin. Welcome to Responsible Conduct of Research, Workshop 4. My name is Catherine. I'll be facilitating this session. I just wanted to tell you that I'm going to be putting some things in chat, and one of them is the workshop series basically list. You can go to that site and look at all the workshops that we have for this semester. I'm also going to be placing in there something for a micro-credential in responsible research if you're interested, and that comes straight to me, my email address, and you can complete that on your own time whenever you'd like, as we are flexible with turnaround time with that. Finally, I'm going to be putting in the chat towards the end a couple of times a survey. So please make sure you complete that evaluation, because basically we report it to our funding sources, and it really helps to continue getting us funded and also allows the presenters to make changes based on needs for future presentations. So we really appreciate that. Today, we're going to be learning about responsible data acquisition and management. We have an expert here, Dr. Peter Elkin, who's professor and chair of the Department of Biomedical Informatics and professor of internal medicine at the Jacobs School of Medicine and Biomedical Sciences. Again, if you have any questions, please type them in chat, and I will address our speaker with them at the end of the presentation. And I'll turn it over to Dr. Elkin. Welcome, Dr. Elkin. Thank you for coming.
Thank you for having me. I'm just going to share my slides. So as introduced, I'm Peter Elkin. I'm an internist by clinical training and a clinical informatician by boards as well. And in addition to that, I have a research area that's in biomedical informatics, and I chair the department here at UB. And we're going to talk a lot about responsible data management. And this is very important if you're thinking about a career in research. This is a way to keep you safe as you go through your activities of daily living and your research tasks. So I have no conflicts of interest with this talk. Our learning objectives are to understand how to ethically handle data, understands one's responsibility with respect to research data, to understand what constitutes an unethical data management, and to understand HIPAA and the consequences of unethical data management under the HIPAA law, to understand how we deal with fair data, and to understand what constitutes ethical data reporting. So Hippocrates said, even way back when, whatever in connection with my professional service or not in connection with it I see or hear in the life of men, which ought not to be spoken of abroad, I will not divulge, as reckoning that all such should be kept secret. Short way is, that health information is a protected class of information. It's confidential, and especially when you have access to a lot of it, it's really important that you keep that in mind. So we're going to talk about unethical data management first, so that you can kind of see in the context of what best practice is, some of the ways that things have gone wrong for people. So we'll talk about fabricated data, biased methods, fishing to find positive results, not publishing negative studies, unauthorized release of protected health information, merging unrelated data, splitting one's record into two research IDs, and using unreliable data to try to generate reliable results, and a special codicil on mobile systems. So here's a article that was retracted. There's a retraction index. There's increased pressure on faculty to publish and obtain grants. Many trials prove that interventions do not work. Recruitment to clinical trials is hard, and trials are often at least 6 months behind. Retention in clinical trials is also an issue. And remember, as a scientist, your word is your bond. I mean, that's what we really have, is that people believe what we say. This is a particular paper on fecal transplants and obesity was retracted. And it linked fecal microbiome to obesity, has been retracted after it became clear that the authors faked some of the data. So it was said in a report published in the Federal Register, so everybody got to see it. To produce the results desired by the researchers, false data was submitted. and further grants were obtained. That 6 of 33 patients responded favorably to the test when only 4 patients were enrolled in the trial. None of them responded positively, and this was published afterward when this was retracted. Even though Diabetes is a very good publication, it was published, the retraction was published in New England Journal of Medicine, Nature Medicine. Oh, that should have been JAMA. So it's really a much bigger deal to get it retracted than it was to get it published in the first place. So why does this happen? Why do biased methods happen? Well, choosing your population on which to intervene can be biased. Choosing your controls can be even more biased and often is wrong. Non-randomization in trials, unblinded tools. Some statistical methods are more sensitive than others, so picking them to get the answer you want. Type 1 error, which is error by chance alone, is a real problem and creeps into a lot of people's studies. And this has to do with fishing for positive results, where the study was not architected to study that outcome or was powered to differentiate that outcome from its alternatives. So here's an example of a sample that's not reflective of the entire population it's sampling. And when you think about this, there's the whole population, there's the sampling frame, there's the actual sample you get, there's a response error and the actual response. So it can be very hard to get a unbiased study. You have to work hard toward it. So one of the things that I see a lot of is error due to fishing to find positive results. So researcher doesn't get the answer they want for the main outcome that they've architected in their study. So they say, what can we make out of this data? They try to use one design to answer a question that requires a completely different design. And answering a question in a subgroup analysis that your study was not designed or powered to answer is going to give you false results. And then you have to, if you're asking lots of questions, that increases your chance of getting a false positive result on the basis of chance alone, which we call type 1 error. So what do you do with these negative results? Well, often they don't get published. I'm not going to actually read you the slide. You can read the cartoon. But the point is that editors are more and more tasked, and I'm the editor of a high impact journal. I can tell you to accept negative studies. But if you really look at the data, that if you have strong results, it's much more likely to be published, and it's much more likely to be published in a top journal. If you have mixed results, it's less likely. And your null results, they often are not published. Look at the unwritten is over 60%. So HIPAA is a law. It's the Health Information Portability and Accountability Act. It has a codicil in it, which is the Administrative Simplification Act, which provides not only that you should keep patients' data safe, but in addition to that you should actually be responsible for any release of information that is not one that's agreed in the law that you should be able to do. So the penalties are pretty severe. It can be up to over $2 million per violation. That's per physician per year. And so if you have lots of patients, they can, amount up. It used to be it was infinite, but now it's down to each doc can be charged $2,190,294 per violation. And that's from multiple people's records that you had being released. And they can also impose criminal penalties where they feel that this was willful neglect, like a tier 3 or tier 4 exposure. The 4 categories are covered entities like a hospital or a physician, somebody who is supposed to keep their data safe. And if they're trying hard, but it happened anyway, someone hacked into a site, nobody could have seen it coming, you're kind of in tier one. In tier two, you had a problem like you didn't put patches on your software when you were supposed to, and so you had a violation and people were able to hack your system and get the data. That's like a tier two. Willful neglect is you haven't updated your servers in years and you should have you're actually not doing what you're supposed to do to keep up. And then if you find out that this happened and you don't correct it within 30 days, it becomes tier four. And that's where you could go to jail, actually. And here's another one that actually, I can't believe that this is not in the front, but it should be. So covered entities that experience a breach affecting more than 500 residents of a state or jurisdiction are, in addition to notifying the affected individuals, required to put a notice in prominent media outlets serving the state or the jurisdiction. So if I did it, that would mean that my face would be out there with a breach in the newspapers, and so it can be a very career damaging thing. I've been heard tell that it's brought down deans, and I can tell you that that deans are very serious in general about this kind of release of information. And then, so that's a significant penalty, and it's a reputation killer. So really pay attention to this. So merging unrelated data. So how many John Smiths do you have in your population? If you have a different medical record number at each of the hospitals that you see patient, how do you know to combine that data, or do you consider them separate people and your N becomes much larger, and then all of a sudden you've got errors in your system about assignment of facts to those people? We did one study where we showed that the error rate was 36.1%. But if you look at the entire literature, it spans from between 23% and 40%. And I can tell you that the 40% number, which was out of Europe, was much more likely to be true than the 23% number. In addition to the false negative rate, there's a false positive rate as well with data, making the total error sometimes up almost 2/3. That there are really problems with data that make it difficult to combine. Lab names are non-standard. Most people don't use LOINC. Medication names have now become standardized, but not everybody's adopted it. And so that leads to difficulties in doing things. NDC codes, which are codes that are used to purchase meds, they can be reused by a company. They're doled out in lots by the FDA to companies. And that can lead to error where you have the two different drugs have the same, NDC code. So if you can't figure out that this patient is the same patient from two different organizations like Kaleida and ECMC, you could split them into two patients, and that can also create error. Sometimes you're combining people that have the same name that are really different. And in this case, you're splitting a person into two IDs. And in that case, you are having much more trouble in terms of the data quality. Not knowing that a patient has passed away also can be problematic. In our practice plan data, we had a whole bunch of people that were in their 160s. And I got to tell you, either we're given the best care in the world, or maybe they just didn't know that some of these people had passed away. And I'm just saying that we need this to be more available and needs to be monitored more carefully. So you can't use unreliable data to generate reliable results. Garbage in, garbage out. Know your data. Good data stewards and data scientists make a huge difference. Do as many types of cross-validations as you're able to. So if I wanted to say somebody was diabetic, having a code in the record, an ICD-10 code for it might be one way. But if I see that the person also has a high hemoglobin A1C, and then I also see that it was a diagnosis in a doctor's note, and then I also see that the patient is on insulin. Now I'm pretty sure I have a diabetic. So do as many cross-validations as possible. And of course, there's a general lack of interoperability. We don't use ontology properly in order to identify the facts that we have and to combine them in ways that are important for us understanding that we are able to combine data from different sites. And people are not just seen in one place, they're seen in multiple places. Little note about laptops, that includes all mobile devices, smartphones, flash drives, etc. When you're going to put data onto a mobile device, you have to have certain responsibilities. You need to ask yourself, first, do I need this data on this device? And if not, don't store it there. If you do, then encrypt the data with a strong password. Do not store the password on the same device as you encrypted it on. Put it somewhere else. Report any loss of the device immediately. It's your responsibility to do so under the law. If possible, scrub the identifiers prior to loading the data onto the mobile device. That lowers the risk. Know where your devices are at all times. Do not use the same device for other purposes like family pictures or other things. So let's talk about better practices now, like ethical data management. What do we want you to do? Well, we want you to de-identify the data as per HIPAA, and we'll tell you a little bit about that in a minute. We'll talk about trusted brokers, two people being required to release identified data through IRB approval or a public health emergency. We'll talk about encryption, firewalls, and inhibit hacking and two-factor authentication, which we now use at the university. We'll talk about fair data principles, data-driven recruitment to clinical trials, which is really up and coming. This is great. E-consenting, electronic data capture in case report forms, adverse event reporting, and results reporting in general. So let's start with fair data principles. So in the F in FAIR is for findable data. Metadata are assigned a global, unique, and persistent identifier. Data are described with rich metadata. The metadata clearly and explicitly includes the identifier of the data it describes. That metadata are registered or indexed in a searchable resource. The A is for accessible, and this is where metadata are retrievable by the identifier using a standardized communications protocol. The protocol is open, free, and universally implementable. The protocol allows for an authentication and authorization procedure where necessary. The metadata are accessible even when the data no longer exists or no longer are findable, so people can go back and see where that data was. Interoperable. Metadata use a formal, accessible, shared, and broadly applicable language for knowledge representation. The metadata use vocabularies and ontologies that follow the FAIR principles. The metadata include qualified references to other metadata as is needed to really understand the meaning. And reusable. Metadata are richly described with a plurality of accurate and relevant attributes. The metadata are released with a clear and accessible data use language and license. The metadata are associated with detailed provenance, which means you can tell everything that happened to the data from when it was created till when it exists now. And the metadata meet domain-relevant community standards so that we have enough context to understand it. So HIPAA de-identification, there's really in the privacy rule, which is part of the HIPAA law, there's two ways to do it. One is expert determination, and the other is called the safe harbor method. And I'm going to describe them both. So in the expert determination, this is where you use statistical methods to take out random amounts of data until it's unidentifiable as would be determined by statisticians, a group of statisticians. Almost nobody uses this because it kind of destroys the data for research. The safe harbor method takes out 18 identifiers. These are the 18 identifiers that are there. I've got them listed right here. I'm not going to read them all to you, but you can see that there's some things to point out. One is that if you have a zip code with less than 20,000 people, you need to change the zip code to 000. And so you can't, get around this. And everybody who's over 90 needs to be in a category 90 plus because there are less people, right? So it's easier to re-identify people. And this is what HIPAA de-identification is. And I'm going to talk for a second about, before we get into trusted brokers, about limited data sets. So there's a couple things on here that's very hard to do research without. One is location, zip codes, which sometimes can be problematic. And often you get 3-digit zip codes only, but it'd be nice to do better. The second is dates. It's almost impossible to do research in biomedicine without dates. And the reason is that, things are usually longitudinal and longitudinally related. Some people have tried date shifting within a 90-day period across everything, but eventually you'll be able to put it back together. And it turns out that is a bit of a fool's errand because given 10 facts of dates, you can match things up with the same distances between them and do a pretty good job re-identifying people. But there are a lot of things that you're getting rid of, like social security numbers, IP addresses, medical record numbers, that it's very easy to do, email addresses that you don't want to do it. The other thing that is not part of this that's important is location. We published a paper showing that we can re-identify people with car accident data based on the location of the car accident and location information in the notes. And it's pretty easy, actually. So it's a little scary out there how easy it is to find people, especially if they're pretty unique people. So if we said, the coach of the Buffalo Bills, I think it'd be pretty easy to figure out who it was. If we say the mayor's wife, in Buffalo, it's pretty easy to know who it is, even though these are not HIPAA identifiers. So you have to use a little common sense as well as you're creating these data sets. So the best way to do it is what's called a trusted broker design. As the data is de-identified or made into a limited data set, a research ID is assigned to the research data. The research ID is a meaningless ID, but it connects all the data that's related to that patient. A table is created on like a clinical system that the crosswalk between the real ID and the research ID can be had, where you have the right to see that data. And this crosswalk table never leaves the clinical system and is not part of the system that you're doing research on. It's encrypted and secured, and it takes 2 people to break the seal on it. Somebody who has access to the file and one who can unencrypt the data, has the unencryption password. These can be done under only 2 circumstances. One is IRB approval, and the other is a public health emergency with a request from a bona fide public health agency, and that's as specified in the law. And this is really important. So if, for example, you did a retrospective study and then you wanted to do a prospective trial and you need to find out who those people are, you could still do it with IRB approval, but it actually achieves much of the goals of having the identifiers, but without putting people at risk on that particular server from data that was easily turned back into a way to harm others. Well, let's talk about encryption for a minute. So this is a few years ago, but it was said that it takes the NSA about 24 hours by brute force methods to break a 48-bit encryption key. It's probably about the 256-bit encryption key now. And for a while, you couldn't send health information out of the country encrypted more than 48-bit. But they decided that the health of people and their security and privacy was worth more than national security. They were worried that somebody who was a terrorist would send messages in health encryption data. And now the standard is 256-bit encryption, which is harder to break, but it actually is very expensive to break. And if you look at the value of the data versus the amount of effort that you'd have to put in to break a 256-bit encryption key, it rarely would be worth it. Even if you take a very famous person, President of the United States, whatever, it would be a very large cost. And interestingly, now we encrypt our data without slowing it down. The encryption decryption is so fast that you don't even see it. And so it is there's no good counter argument to having your files encrypted. So there's nothing you can say that will get the judge that you're before or after you've had a breach to not hold you responsible for that when you didn't encrypt your data. And you can not only encrypt the whole disk, but you can encrypt particular files. So even if you didn't want to encrypt the operating system or whatever, you could certainly encrypt the data itself. The goal is the cost of de-encryption is greater than the value of the data to someone trying to get at it. And what we try to use is a symmetric key or private key so that we use a public key infrastructure. And the way that works is if I wanted to send, pick somebody on the screen, Samantha, a message, I would use her public key and I would use my private key to encrypt it. And she would use my public key and her private key to decrypt it. And it gives an extra layer of protection because in order to have my public key, we had to agree that we were going to talk to one another ahead of time. So firewalls are to prevent hacking, and we need more and more of them, and not just on computers, but on printers and everything else. We had our printers hacked in the department, and the worst racist stuff was coming through. We had to chase down how this was happening, and it turned out it was happening all over the university, and even the computer science department was hacked at that time. And we put firewalls on every electronic device. We were very, and we haven't had a problem since we did that. So you want enough firewalls that you can actually stop everything. So in our case, where we live in our building, there's a firewall around UB, there's a firewall around the building, there's a firewall on our floor, and there's a firewall around each of our computers. So we think we're pretty safe because we've taken extra effort to ensure this. So you have to know both the user ID and password to get access to the site. Plus, you have to understand the port ID that's open because when you specify rules for a computer of who can access it, you give it an IP address and a port address that would be open. So we have a large language model that's the best medical question answering software on the planet. It's better than Microsoft, better than Google, better than everybody. And the NIH actually told those companies that we were doing better than they were. And we have that encrypted, and it's on its site. And there's only 2 ports open. One is for our people to get in and do work on it, and the other is to get to the interface, which is sitting on a web server, which doesn't have any data. And so it's very secure. So and each of these, you can put on there even a list of sites that are allowed to access it. So, for example, on our machine, those ports aren't like widely open. Those are ports that are open, and they have a list of people that are allowed to get into them. And that's the only people that they will allow in no matter what. So we've preordained what will allow people who will allow to access our machines. So two-factor authentication is the way we do things at the university. And they've cut back a little bit, like, for instance, in the Zoom call, Once I put in my email address, it didn't ask me to put in my password or go to Duo in order to get in to give this lecture, but it does for many of the sites that I use at the university. If you're going to input data or get access to sensitive data, it certainly should. And sometimes it requires a physical token. I have one for the the Department of Energy machines, and that has a physical token. And I don't know if you can see me, right? So, oh, this is the physical token they gave me, just to give you a sense of that. And you can push it and get numbers out that you have to put in to help you reach those pieces of equipment. And always avoid identity theft, reaching your data. If you don't know the site or whatever, don't go to it. Don't buy things off it. Putting in your credit card's a little risky. So often people use PayPal instead. That's a little better. But there's so many people trying to get your data. And if some Nigerian prince wants to give you $12 billion, they're not real. Don't click on it. If you get an email thing and the email has an attachment that says, I love you, that's a virus. Don't click on it. That caught so many people all over the world. There were ransomware attacks, all kinds of things when that virus came out. Apparently, we all want to be loved. But the bottom line is that if it doesn't seem reasonable, just today I had guys want to give me various amounts of money, just give them my credit card accounts. One was like $359, the other was $4,000 and some odd, and none of them were real. And I just deleted the emails. If it's too good to be true, it is too good to be true. Don't get fooled. Here's a number that might be interesting to many of you. We have at UB 60 attempts to hack our computer systems at UB per hour from China alone. 60 attempts from China alone. So, this is going on. Just be careful. So one of our politicians had this in his office, and I believe you need data. I trust data. I believe in facts and figures. So this is something you don't see every day. This is so about, I don't know, maybe 10 years ago, ECMC got a ransomware attack, and people clicked on it and it opened up the virus. And then 6 months later, so it encrypted everything on their computer using a private public key infrastructure. And this is the ransom note that they got exactly. This is the actual ransom note. So what happened? Well, here's what happened. Well, they were mad. They were angry. They didn't like it, and they didn't want to give in to these people. They thought they were bad people, and they were not going to do that. So they went ahead and tried to replace all of their computers with fresh builds. And they brought up the computers, and sure enough, it was still encrypted. They had put in there a delay, so these things were on the system for a long time before they actually triggered. So it just triggered again. So then one of the doctors at ECMC had got a message for their PC, very much like this, and they paid the ransom. It was 1.7 bitcoins, which at that time was worth only about $2,400, and he paid the ransom. And he got a code, and he put it in, and it worked. It opened the system, and he got it back. So he shared the code with ECMC, and what did ECMC do? Well, they figured that's the only code that this company has, so they tried to use it. What do you think happened? Deleted all their data. Skull and Crossbones came up and started deleting data everywhere. Well, they had some backups, but they lost 6 months of data that they had to rebuild doing that one. So the CIO got fired, that's no question. Oh, by the way, they were asking for 24 Bitcoins. 24 Bitcoins was worth at that time, I think, about 30 some odd $1,000. In the end, they spent over 10 million getting their computers back. and and I'm not sure it was worth it. Um, and this is how decision making sometimes can go horribly awry. Um, anyway, this is a ransomware attack from a public-private key infrastructure. The same thing we told you before when I was communicating with Samantha, only it was done for nefarious purposes. But they didn't pay them. So here's a little thing for me. So we have natural language processing software, and we use it to pull out codes from people's records. And it is, in my opinion, this is easier to accept being shipped around for each person, and it has all the information you'd ever want to know about how to do research on them. But it's easier than actually putting the text note that has all of those non-HIP identifiers in them and produces that risk. So we're advocating that NLP be used, or natural language processing, to pull out this kind of coded information and then built into networks, and that be used by researchers in order to do their research. So this is the architecture we put in place that would be an interoperable architecture for our CTSA that led to the first approval of the CTSA by NCATS. And it actually is a principled, secure infrastructure that has physical interoperability, platform, standards-based, and application-based interoperability. So now I'm going to talk a little bit about data-driven recruitment to clinical trials. So there's now these real-world evidence studies. I don't know if you've heard of those, but what that means is that instead of having a protocol where you have a doc who goes in and sees people at particular intervals and records the information in a case report form, which is how research was done forever prospectively, that we actually use the data that's in the medical record. And that would allow us to do over a much greater distance, recruit people, so that we can take even rarer things and be able to do research on them over a great distance. And we do it by putting in the inclusion-exclusion criteria and then having a critical question that we want to ask. We get e-consent from the patient, and we use that with the 21st Century Cures Act and the information blocking codicil that says that the hospital has to give you the data, no matter who they are. And they don't actually have to be part of the study as long as the patient has given their consent, because the 21st Century Cures Act says that that's your data. That's not the hospital's data. It's yours. So you have the right to decide who gets it. And so there's an exception to that, where the IRBs can give you access to data that's retrospective as well, and they often do, but even without patient consent. But with patient consent, you always get the data. That's the key. The real world evidence says that using Smart on Fire, which is a protocol for how to access data at different institutions using a common set of terminology, allows you to go in and access the data using a common set of methods, and then get that data, combine it, and use it in a research study. And you can do it at various points in time within the study, and then be able to get what information is available at that site for that patient. And then do a lot of data cleaning and WOMPing in order to make sure that you have enough data to get a longitudinal idea of what happened to the patient with or without the intervention. Sometimes interventions can even be interventions where there's a mail order pharmacy that sends drugs and tries that against a placebo. And so even randomized double-blind placebo-controlled trials can be done with real-world evidence. This is becoming more popular. It's faster to recruit, and it's faster to get the answers. And it costs less to do it. Right now, if you do a regular prospective trial, it costs approximately $1 billion for one prospective trial. And half of those trials are 6 months behind. And that's a cost of $500 million so there's a lot to be gained by doing these real-world evidence trials. Here's an example. We have a tool that people get access to. It's called the BMI Investigator. Someone came into my office and they said, I think my patients who have rosacea have a higher rate of obstructive sleep apnea. So we did a study in 5 minutes and showed it was true. So the chance of obstructive sleep apnea without rosacea was 2.6%. And the chance of obstructive sleep apnea with rosacea was 8.8%. That was highly statistically significant. And more importantly, the relative risk of obstructive sleep apnea was 3.4 times with the rosacea. And the number needed to test was only 12. So what that means is that everybody with rosacea should be asked the screening questions for obstructive sleep apnea. And we published that, made a difference in medical care. And we did it in 5 minutes. So it's kind of a neat thing to be able to do. Here's an example of how you get the de-identified data with our tool. And you can put it in, and it allows you to recruit over one period and look at outcomes over another and the whole bit. So it's very, and you can look up lab data or medication data or diagnoses or anything you want. It's pretty detailed, but you don't get who you're talking about. They're actually research IDs like we're talking about here. But immediately you can get information out like race, ethnicity, gender, and age distributions automatically. Kind of a neat thing. So here's another 5-minute study. We thought that one was too easy, so we decided to do another one. This is the question is, and I'll ask you guys, but you can tell me if you think you know. But I can tell you I've asked this question in ID audiences when I presented this in national and international fora, and nobody knew the right answer. So let's say you get the flu shot and you still get the flu. Did it give you some partial protection, or did it just miss? So the way we went about trying to answer the question was we looked at a complication of influenza, which was pneumonia. And we controlled for things like pneumovax. And we ran it in both people who were vaccinated and unvaccinated, but all had influenza. And when we looked at it, what we found was that there was absolutely no difference in the risk for pneumonia between the groups that were vaccinated and unvaccinated. So at least in this cohort, it didn't, if you missed, it missed and didn't really prevent you from getting pneumonia any more than you had before. Then we said, well, okay, let's say you have pneumonia and influenza and you're a smoker. Shouldn't someone tell you to quit smoking? I mean, seriously. So we looked for that because we had natural language processing software that could look into the text. And only 2/3 of the people in this study were told to quit smoking. Well, we put in, programs for continuous quality improvement to try to improve that because we thought that was unacceptable. And it was a very high-risk group, right? And then, of course, we looked, and as we published this, we looked, and there was absolutely nothing in the literature before us about this. So it was completely novel. So let's talk about a few other things. Well, there's e-consenting, I mentioned that, and informed consent is a process, not just a form. Information must be presented to enable persons to voluntarily decide whether or not to participate as a research subject. It is a fundamental mechanism to ensure respect for persons through provision of a thoughtful consent for a voluntary act. The procedures used in obtaining informed consent should be designed to educate the subject in terms that they can understand. Therefore, informed consent language and its documentation, especially the explanation of the study's purpose, duration, experimental procedures, and they call everything a procedure in studies, alternatives, risks, and benefits, must be written in lay language, understandable to the people being asked to participate. The written presentation of information is used to document the basis for consent and for the subject's future reference. And it has to be people who can give consent to the study. So I'm going to stop and digress a second. So I was reviewing a grant where somebody was trying to get retrospective data on Alzheimer's patients. And they used an opt-out strategy, which meant that if they opted out, they could opt out, but if they didn't opt out, then they were automatically in. And I questioned whether that was ethical, because how can a Alzheimer's patient opt out? If they didn't really have the chance to opt out, to understand and opt out, they didn't really get the chance to make an informed decision. And so I brought up ethical concerns with that study. The consent document should be revised when deficiencies are noted and when additional information would improve the consent process. Use of the first person, like "I understand that," can be interpreted as suggestive and may be relied upon as a substitute for sufficient factual information and can constitute a coercive influence over the subject. Describe the overall experience that will be encountered. Describe the benefits that the subject may reasonably be expected to encounter from participating in the study. Describe any alternatives to participation in the study or research project. The regulations insist that the subjects be told the extent to which their personal identifiable information will be held in confidence. If there is research-related injury, and that doesn't have to be physical, it could be psychological, social, financial, or otherwise, is possible from the research that is more than minimal risk, an explanation must be provided of whatever voluntary compensation or treatment will be provided for that harm. Note that the regulations do not limit this to physical injury. So if you've got a study on something like HIV, that could be traumatic. And that is something that you need to probably get informed consent. The regulations prohibit waiving or appearing to waive any legal rights of the subjects. Had a funny story. I like to do escape rooms. My family does. So we were going to this escape room and they gave me a consent thing to sign that said that they could kill me on purpose and it would be okay. And my son, who was a lawyer, said you cannot waive that right. Nobody is allowed to waive the right to unreasonable treatment. And so they were still liable if they were to kill me on purpose during the escape room. The regulations provide for the identification of contact persons who would be knowledgeable to answer questions of subjects about the research, the rights as a research subject, and what will happen with research-related injuries. And these three areas must be explicitly stated and addressed in the consent process and documentation. And there must be a statement regarding voluntary participation and the right to withdraw from the study at any time. So let's talk about electronic data capture for a minute. Electronic systems that capture data related to the study must take into account the user's perspective, and we must use user-centered design. If they are collecting data, the data collection method must be referenced in the IRB and approved. New forms should undergo usability testing. Data types and data questions should match your IRB approval. Questions should be codified in a standardized coding system so that they can be reused once validated. Possible answers should be codified in a standardized codifying system so that they can be linked with the questions. And that groups of questions that have been validated cannot necessarily be delinked and reused as smaller abilities. And we actually made that happen as constructs within the patient safety standards that the country now uses, because people were trying to pick and choose line items that they wanted to use, and that is not okay and could lead to error. So usability is an important part of this. And if you look at usefulness of the whole system, there's the utility of the system, but there's also the usability, and that is about easy to learn, efficient to use, easy to remember, few errors, and yes, be subjectively pleasing. If people identify with it and like using it, they'll be more likely to use it. Let's talk about case report forms for a second. Reports and report form filing is required for all unanticipated problems that arise in the research, and that includes a data breach, and all adverse events that are more than minimal risk. So here's an example of a case report form that's from the CDC. And you can see this is a babesiosis case report form. And you have to fill it out if you had a problem with the study. I'm not going to read the joke to you, but I'll just leave it there for a second. I'm sure they get it. Okay, moving on. Adverse event reporting. So here's the basic flow of decision making. So if you have an adverse event, did it occur in one or more people? Is the adverse event unexpected in nature, severity, or frequency? And if it's no, then you can stop. Is the adverse event related or possibly related to participation in the research? Because things happen to people that may be unrelated, and if it's no, you can stop. Does the adverse event suggest that the research places subjects or others at a greater risk of physical or psychological harm than was previously known or recognized? And if the adverse event is serious, the answer should always be yes. But if it isn't, then you can actually decide whether to make it something that's reportable. So once you get the results of a study, you should always publish your main outcomes, even if they weren't significant. So if you're publishing something else, some subset analysis, and you have to be powered to be able to do it, you should redo your power calculations, then you should also report the main results as well. Never let your conclusions extend beyond your data. This happens all the time. I'm an editor-in-chief of a high-impact Q1 journal, and only 2.5% are Q1. And one of the biggest problems I see is people making claims that extend well beyond what their data shows them. Make sure your methods, results, abstract, conclusion match in both breadth and content. Nothing annoys an editor more than a disjointed article. And we should definitely be increasing our results, and the reporting of negative results is a priority. So then we think about plagiarism. There's a lot of plagiarism going on, and now we have software to kind of check whether ChatGPT is writing your paper or not. And we, all these paper mills and whatever, we're able to find them in journals, and we stop people. And if you get on the no publish list, you can't publish in that journal, and anybody who publishes with you gets linked to you, and they, whether they can publish or not, that paper certainly will never be published in that journal. So I had a guy who was on that list, and the authors go, "Hey, if we take their name off, can we publish?" I said, "No, if you thought that person contributed enough and they're a cheater, we do not want them. We do not want that paper in our journal. Go somewhere else." So, these AIs, they often have confabulation, and some people think they're just plagiarism engines. So they're only putting out stuff that they've seen before, because it's based on their training. However, now we've been able to put in new methods of reasoning, so I think you're getting some novel things out of these. There are co-scientist programs that are trying to create novel hypotheses that no person has ever generated before. And I think it's not much time before these become sentient and have rights of their own. And we're going to start to see this, certainly as robots, but I think you're seeing people will be thinking of the practice of medicine as a patient, a doctor, and a thinking computer as partners in care. this changes liability. It changes everything about the practice. But the hope is that it'll bring authoritative information to places where it wasn't before, and to make care more egalitarian around the world, and to decrease bias by bringing authoritative information everywhere it needs to be by a source that is just thinking about what the best thing to do is and not any other influence. So this is a CTSA thing. This is about translational science, informatics science. And this is studying methods to improve the ability to recruit people to clinical trials, studying novel informatics methods to improve clinical trial recruitment, also studying methods to improve collaboration and mentorship, and novel methods for improving data science training and pilot studies, and then studying information science and uses of technical interventions to improve our ability to deliver information to clinicians and also to patients, and also to practices more rapidly. Systems designed to capture clinicians' ideas so that we can actually go from not bench to bedside, but bedside back to bench. It is a good idea. And I think, honestly, that these are important areas. Also, I think for the meanwhile, what you're going to see isn't that AI is going to replace doctors, but that a doctor who uses AI may replace a doctor who does not. So you see a lot of things with these deep fakes and generative adversarial networks, even things that never would happen in real life. And this is how they do it, by the way, just to give you an idea. So here's this cat, and you're adding noise to the image. And as you're adding the noise, it's also learning how to denoise it at the same time. And it's this basic idea that diffusion models like this that are how generative adversarial networks work. So here's an example of there's me. I put it through a generator. This is what it thinks I look like. I put it through the discriminator and iterate it a few times, and it's getting a little closer. And then I keep iterating it through the generator, and eventually I get to a GAN model where it can put me wherever it wants. So we use ontology. That's the thing we use in UB. And the basic formal ontologies are upper level ontology. We use the ontology of general medical sciences for our courses of illness. And then we use SNOMED, LOINC, and RxNorm as the detailed ontologies underneath it. And then we create networks or sentences out of this that are codified that can be reused. And what we did was we had this idea, even before there were large language models, that if you were looking at data and you were an AI, why shouldn't you have the same advantage a doctor does? A doctor has all its medical training, all the prior cases it's seen. So why can't we give some prior medical knowledge to these AIs and see if it makes their work more accurate, less biased? So we changed it on how we speak in medicine, on evidence-based medicine, the medical literature, all drug information, all toxicogenomic information, a whole bunch of other things. And then we used that to build models to predict. We had a database of 170,000 people that were opioid users, and we looked for overdose and death events. And we found that with the pre-trained embeddings of medical knowledge, it was not only more accurate, but it was also less biased. So if you look at, as we take data away from the model, or randomly take data away or people away, that the curve at the bottom degrades more rapidly, which is just the model built off the exact same data, but without the pre-trained embeddings. And the top one is with the pre-trained embeddings, and you can see that it's better. And so we decided to test this, and we did and published a JAMA article, and I wanted to see how good we were. And this is actually our old data that I'm going to show you. And this is how it works. Here's another way. This is a picture of of the embodiment of our AI. And so we go from a model into these codified sentences We put it through our large language model, and it comes out with facts. We have 33 million facts and then we put it through a regular large language model in order to look at it. This is an example of a bad answer. This is a prompt that we gave it, and then it gave the answer that the base model that reassure the patient that her symptoms will resolve in time, which is wrong. With the pre-trained embeddings, we put all these facts in, and then it says recommend behavioral therapy. So I probably should have read the case. This is a 24-year-old college graduate who comes because of 3-year history of increased frequency of urination and occasional incontinence when she travels. She says that her urinary symptoms typically begin a few days before she's going to fly, and then they stop when she arrives at her destination. She says she's anxious about flying, and she reports having a similar but milder symptoms prior to exams before graduating. Her medical history is unremarkable. Her only medicine is oral contraceptives. Vital signs are normal. Physical exam discloses no abnormalities. Urinalysis and urine culture are normal, and then it's giving you these choices. So again, wrong answer from the regular LLM. And when you put Sky in there, all of a sudden it gives you the right answer. And here's the data from the first study, which shows that we were able to improve all of the different llama models at different sizes. And the llama 70 billion and 405 billion were not statistically significantly different. So we put up the 70 billion model, much cheaper to run for us. And now all kinds of people, 48 countries are using it, 130 organizations in the US, the federal government's licensed it. It's up and running. And then now we've got newer data that shows that on the step 3, US medical licensing exams, which is the most clinical of the study, got 98.4% correct. That's actually in the top 1% of all clinicians. So it's really good. I'm also on the FDA's Digital Health Advisory Committee, and we got model cards to be enacted as part of the regulation to include, training population methods, evaluation, so that people can be aware of what these AIs are supposed to be good at, and not just use advertising to figure out what they should do. This is the Gartner Hype Cycle. We are up here right now where people are really excited about AI, and we're headed directly to the Valley of Death here, which is what happened in 1991. And what we need to get over to a stable computing environment like here is to have good randomized prospective double-blind placebo-controlled trials that show that these are useful and can get into clinical guidelines. We give a data science boot camp every year, and it's for free. You can just sign up, look for a data science boot camp, and we increase it in terms of the number of talks every year by a little bit, and it's fun. We've had great response. We had 743 people take it last year, and it's been very exciting to see the growth of the program. People at NIH take it. It's really good, and it costs you nothing. You get on to a Jupyter Hub and use Jupyter Notebooks to really learn how to do data science. And so if you're interested, please do sign up. I'm the editor-in-chief of the Journal of Translational Research, and I should put in here, but I'm now the editor-in-chief of the Journal of Biomedical and Health Informatics, which is an IEEE journal and has an impact factor of 6.8, a citation score of 13.5, and an H-index of 168, which puts it in one of the top journals in the world. And my favorite quote is from Peter Drucker, who said, "The best way to predict the future is to create it. Come create the future with me." Now I'd like to have some discussions with you. So these are all fictional cases, but Socrates said the following. I really like this quote too. "Strong minds discuss ideas, average minds discuss events, weak minds discuss people." Be a strong mind. Okay, so here's the first case. And I'm going to ask one of you to be the reader and another of you to be the discussant. So who wants to be the reader of the case?
Anyone try to read, please?
I can read it.
Oh, thank you very much, Jordan. I appreciate it.
A young researcher is analyzing identified data from a clinical trial on her laptop which she carries in her backpack. She always keeps her backpack carefully protected. She stops to go out to dinner with a friend, and she locks the backpack in the trunk of her car. After dinner, when she comes back to her car, the trunk was broken into and her backpack with the laptop is no longer present.
So thank you. And would somebody like to say what the right answer is and why?
So if anybody thinks it's 1, 2, 3, or 4, go ahead and put it in chat. We have a 4. She had 260 patients in the registry. Laptop was encrypted, so she had to report the breach to the study, but not to the newspapers. Anybody else have an answer? I think we're going with 4.
Okay, so that's not the right answer.
Okay,
It's
another person
actually,
for
it's
it.
actually,
1.
I'll tell you why. So, so it's actually 3 because
Okay.
it was encrypted and it was less than 250, so you didn't have to report it to the study or the, well, actually, oh, no. Oh, no, it is 4. You're right. I'm
Okay.
sorry. I apologize.
You want me to
4 is
explain why?
correct.
Because someone
So
put
it's
1
over
there.
250, so you certainly have to report it to the study. But it was less than 500 people, and so you didn't have to put it in the papers. All right, good job. Excellent. You guys are great. Better than I was.
Great.
Okay, here's the second one. Who wants to read it?
Someone besides Jordan, please.
I can read it.
Great. Thanks, Larissa.
John is a research assistant, and his boss asks him to provide the study data. He is a member of the study as approved by the IRB and has access to the data. However, he has class and cannot take the data to his research mentor, who is working at his office across the street. He puts the data on a USB drive or thumb drive and asks a fellow student, Doug, who is not in that class and is not part of the study, who is willing to take the drive to his research mentor in the next building. Doug does not look at the data on the drive and delivers it to the professor in the next building, who thanks him.
Okay, who would like to be the discussant? Somebody who hasn't participated already.
Oh, I do have some answers, though.
Oh, you do? Okay.
Well, I do. I'm having a lot of 5s.
Okay, so with someone who gave it a 5, which is the correct answer, tell me why.
Anyone who gave it a 5 like to explain why? I have 3, 4, 5. Okay, great. Thanks, Zach. Great.
So I think it's obvious John shouldn't have shared the data even in confidence with someone who is not a part of the study, who is not under the agreement to protect the data. And it's so clearly John is culpable for the data breach.
And when did Doug become culpable?
I think that Doug became culpable when he took the data, when he agreed to carry the data for John. He should have refused if he knew better.
Yeah, exactly. He should have refused. But when he actually handed it to him and it touched him, then he was in control of that data. He had it. And that's a breach. So he was part of that too. And the fact that he gave it to the mentor who was IRB approved is not, it doesn't get him out of it. So, and if you guys can tell me, but if any of you can afford to pay the government over $2 million, let me know. That's a lot of money, right? I mean, even no matter, how, well, not no matter how rich you are, but most human beings, that's a ton of money. All right. Good job. You guys are perfect so far. All right. Who wants to read this one?
I'll read it.
Thank you.
A researcher is combining data from 2 hospitals. Hospital A is an academic center and Hospital B is a community hospital. The researchers merged the common patients and merged the problem lists, noting exact matches between the two institutions. After electronically merging the data, the researchers asked, on average, how many problems do patients have on their own problem list in the merged database?
Okay, please read the choices. No, you don't have to. People read them on their own, and then put in the chat what you think the right answer is.
Okay, we do have a couple of answers. We have a 4 with a question mark, which is perfectly fine because there's an answer in the chat.
Okay, so could you tell us your logic?
You want to tell your logic?
Well, I've sort of looking between the data sets, it seems like one set has full descriptors and the other has essentially abbreviations. But if you compare the abbreviations to the explicit diagnoses, then you can sort of see which ones appear to be identical, like identify with each other, except for the first one.
So I understand exactly how you're thinking. I say it a little differently. I would say that, in an academic health center, they're likely to give you more specificity about the diagnosis than a community hospital might. So now I don't know if you're a doctor, if you, Zach, but so congestive heart failure, one of the types of congestive heart failure is left ventricular systolic dysfunction, New York Heart Association class 3. So it's a subtype. Same thing with AFib, asthma, hypertension and resistant hypertension, headaches as a general term, cluster headaches, much more specific, and OSA, obstructive sleep apnea, is just obstructive sleep apnea, right? So the question, though, that you don't know from this, and this is why it gets to be so difficult, is can you just assume that the episodes that were seen at Hospital B were the same as the episodes that were seen at Hospital A? They just documented them differently. And it's difficult, right? So my conclusion was they're going to get the wrong answer no matter what they choose here. That's why having very explicit data. So if we have all of our data codified as ontologic data, if it's really codified, then you should be able to understand what the parents are of each of the terms and know if this was selected as a child of the other and that there's a relationship between them. And then you could be exacting about it, and you could actually say that there's only let's say 6 diagnoses or something like that. And that they were just viewed differently by the different specialties. And I think that that's okay. But often we do studies that are counting things, right? That's very common in research. And so you say, well, on average, how many diagnoses does a patient have? Well, in this case, if you just put them by their text, it would be 11, right? And if you did it by their hierarchy, there would only be 6. And if you decided that was way too specific comparatively, that maybe, some of these ought to be separated out from their parent class. And so it is, if you read the chart, you could have a better idea. But for now, you just don't really know, right? It's hard to do. That's why data science is difficult and why people who do data science get paid so much. So, as I think the last figures I saw, the average salary was like 230 grand or something like that for a data scientist. In any case, point is that this is non-trivial. So let me just conclude with a few reflections Always encrypt your research data. Never send the password with the encrypted file. Always send it separately. Do not write password in the message that you're sending a password in. People will know it's a password if they know for it. Scraping programs will find that. Use a trusted broker methodology whenever possible. Take time to understand your data. Do not report false results. If you don't know that it's true, don't report it. Do not let your conclusions extend beyond what your data is showing you. Remember that there's HIPAA penalties, and be careful and understand that if you lose 500 people or more's data, your picture is going to be in the paper along with that, and you're probably looking for a new job, maybe a new career. Avoid local PC databases wherever possible. Use encrypted firewalled servers. And avoid mobile data on laptops, thumb drives, whatever. Encrypt any drive that you use. So responsible conduct of research requires responsible data handling. Responsible data handling involves the generation, storage, transfer, and reporting of data. The clinician's license is on the line if there's a HIPAA breach. So if someone taps into a building I've never heard of at Kaleida and steals data on my patients, it's on my license. Doesn't matter. I'm to blame. Hospitals get tagged too, but I don't get off the hook just because I don't know anything about that IT system. I didn't have anything to do with it. I've never been in the building that was hacked. It's still my patient's data, and I'm responsible for it according to HIPAA. Responsible data handling is every researcher's responsibility. And the Department of Biomedical Informatics at the University of Buffalo and the CTSA are here to help you with your responsible data and management needs. And my name's Peter Elkin. That's my email address, so it's very easy to get me. And I'd be happy to answer any questions that you might have. And I'll just stop sharing so I can look at you as you ask me questions. Well, thank you very much. It's absolutely a pleasure to be here, and it's nice to meet all of you. Thank you very much for coming. And if you ever need anything in my area or you have an interest in informatics, we'd love to encourage it.